Yes. So we have seen what are the force experienced by a current carrying conductor, and that value comes out to be F is equal to VIL sin theta. If I put a vector symbol on top of it, it becomes VIL sin theta times n cap, where theta is what? Theta is the angle between I and D. Or I can say L vector. Yeah, it is the angle between L vector and D. Okay. I, both are same. I itself takes the direction of current. Okay, angle between the direction of L vector and D vector. Now, the next question is, what happens when you have two current carrying conductors placed parallel to each other? So when you have two current carrying conductors which are placed parallel to each other, suppose I have this to be one current carrying conductor and this to be another current carrying conductor. Okay. And let's say the current in both these conductors are flowing in the upward direction. And the distance of separation between them is considered to be d. Okay. So we know two facts from this chapter, that is, a current carrying conductor generates magnetic field. Okay. Current carrying conductor generates magnetic field. And the second is, current carrying conductor placed in magnetic field experiences force. Okay. So these two are the known facts. Right? Now, if I take this as the first conductor and this as the second conductor, and let me consider a point P on top of the second conductor. So magnetic field at point P, okay, listen to this carefully. Magnetic field at point P due to the first conductor is how much? BP is equal to, and remember, these two conductors are considered to be long. Okay. Then what is going to be the value of magnetic field at point B due to the first conductor? BP will be equal to, yes, mu naught I1 divided by 2 pi into the distance B. Okay. Now what is going to be the direction of it? So it will be into the plane of the paper, that is minus theta. Okay. Let me call this as equation number 1. Now, in the magnetic field, produced by first current carrying conductor in the magnetic field produced by the in the magnetic field produced by the first current carrying conductor, second conductor is placed. So the second conductor experiences force, and if I call that force as F with 2 and 1, means force experienced by the second current carrying conductor due to the magnetic field from the first conductor, it will be current flowing in the second conductor into the length of the second conductor that you are going to consider into the magnetic field produced due to the first conductor. That is BP. Yes. Into sine of 90 degrees. Correct? Why? Current is in the y direction and the magnetic field is in the negative z direction. But if you observe, in the beginning, I told you that the conductor that we are considering are long conductors. So you cannot measure the length of them. So if you take the length of this conductor to be capital L, okay, then F21 will be equal to I2 into capital L into what is the value of B1, which is mu naught I1 divided by 2 pi d. Okay. Now, this is in terms of magnitude. So if you want to write the same thing in terms of direction, you write it as F21 vector is equal to I2 into capital L into mu naught I1 divided by 2 pi d in the direction of what? The direction of, you check your notes and tell me what will be the direction of force experienced by it. Force experience will take L vector cross B vector. L vector is in which direction? J cap cross B vector is in the direction of minus K cap. So J cross minus K is going to be, think it. So it will be minus I cap. So force experienced by the second current carrying conductor due to the first current carrying conductor is going to be how much? F21 vector will be equal to mu naught I1 I2 divided by 2 pi d into L in the direction of minus I cap. Okay. Now this L will come to the other side as F21 vector divided by L is equal to mu naught I1 I2 divided by 2 pi d in the direction of minus I cap. Are you guys able to understand this? So this will be the force experienced by the second current carrying conductor due to the magnetic field produced by the first current carrying conductor. Done? Done? Now, I'll give you 2 minutes time. Find out F1 to enter. 1, 2. So find out, try it out. No? Except, are you sure? Try and see. Right. So what is the answer? Did you do it? Tell me. So if I take the first current carrying conductor, if I take this point to be P dash, okay. So magnetic field at P dash is how much? Mu naught I2 divided by 2 pi d. Direction okay. What is F12 vector? I1 into, you consider the same length L? Yes. Very good. Yes. So mu naught I1 I2 divided by 2 pi d into L in the direction of I cap. This is F12 vector. So if you observe, in the case of F21 vector and F12 vector, they both are having the same magnitude, but the directions are different. And one more thing is, since we mentioned that the current carrying conductors are long in nature, what can we conclude? So since they are long current carrying conductors in nature, we cannot find the force on conductor, rather only find the force per unit length on the conductor. Means, if you write down the value of F12 divided by L, it comes out to be mu naught I1 I2 divided by 2 pi d in the direction of I cap, and F21 vector divided by L will give you mu naught I1 I2 divided by 2 pi d in the direction of minus I cap, right? So if you observe, these two are called as the force per unit length. So we calculated the force per unit length, we didn't calculate the forces exactly. Is that clear? Okay. Is that clear? So this is the value. And here there is another important note that we are supposed to make. If you observe, in the example that we considered, the current in both the conductors are flowing in the same direction. So what we can say is, if currents are flowing in the same direction, then they tend to attract each other. So generally, same means what will we think? We think they will repel, right? But here what will happen is they will attract each other. Okay. In a similar way, the currents are flowing in opposite direction. What can you say? They tend to repel each other. So this is another important question they will ask you. Okay. Done. Now see, the next point that we are supposed to discuss is, till now we were discussing about what happens when a current carrying conductor is placed in external magnetic field, or what happens between two parallel current carrying conductors. The next question is, what will happen when you place a current carrying coil in the magnetic field? When you place a current carrying coil in external magnetic field, what is going to happen? Is what we are going to see now. Okay. So, listen. Torque on current loop or magnetic dipole. So, current carrying loops are generally called as magnetic dipoles. Why they are called as magnetic dipoles, I'll explain it later. But as of now, we'll try to concentrate on this diagram and observe. So, if you observe, you have a north pole and south pole present. So, for this north pole and south pole, what is happening is you have placed a current carrying loop in the presence of this external magnetic field. Remember that the magnetic field is going to be from north pole to south pole. Okay. Now, if the current in the coil is flowing in the clockwise direction, for instance, okay, then I can say that this is the first conductor, second, third, and fourth. Correct. Now, what would be the direction of force experienced by the first current carrying conductor? What would be the value and direction of force experienced by the first current carrying conductor? So, what is F1? It is I into L1 vector cross B1 vector, or B vector for that matter. Right. So, F1 in terms of vector is going to be I into, what is the value of L1 vector? So, L1 is B, small b, into what is the value of magnetic field? It is capital B, into what is the angle between them? Sine of 90 degrees. So I into B sine 90 degrees is going to be the value of F1. But if I put the same thing in terms of magnitude, what will it give us? So it should be minus k cap. right? So it will give us minus k cap, right? So let me make it simple for you. Let me make the same thing simple for you. North pole, south pole. Let's say you have a current carrying coil like this. Okay. And let's say the current is flowing in the clockwise direction. It is like this. So if I take this as first, second, third, and fourth conductor, let's say this side is A and this side is B. Okay. So what is going to be the value of the force experienced by the first current carrying conductor? Force experienced by the first current carrying conductor will be I into small b into capital B. Capital B is in this direction into sine of 90 degrees. If I make this as a vector, then what is going to be the direction in which it will experience force? It will be into the plane that is minus k cap. Right? So this will be I into B into capital B in the direction of minus k cap. Now what about F2 vector? Force experienced by the second current carrying conductor. It is 0 because current and magnetic field are in the same direction. Then what about F3 as a vector? It will be I, B, B in the direction of plus k cap. Then what about F4 vector? Again a 0 because angle is 180 degrees. So what is going to be the net force that is acting on the system? F1 vector plus F2 vector plus F3 vector plus F4 vector. Answer is 0. Means this kind of a system does not experience force. So when it is not experiencing force, what can you say? Means it is not going to move. So it has no translatory motion in this scenario. But there is nothing about d cos theta. It does not move. It does not have a translatory motion. Okay. But if I take the same rectangle, okay, if I take the same rectangle and I break it into two equal parts like this, such that the magnetic force is still in this direction. We call this as B. Okay, and the current is still I. Okay, remember here the force is into the plane, and here the force is out of the plane. So this is the direction of force. Right. So if this is into the plane and this is out of the plane with equal magnitude, what will these two forces do to the system? Since the forces on either side of the axis, correct, are in opposite direction. Since the force on either side of the axis are in opposite direction and are of equal magnitude, they form a couple. Hence, the system tends to revolve. Hence, the system tends to revolve. Okay. So when it is going to revolve, when you see from this side, okay, when this is your eye, when you see from this side, in which direction do you think will the rotation happen? Will it be clockwise rotation or anti-clockwise rotation? So it will be having a clockwise rotation. Right? It has a clockwise rotation. Now, when it has a clockwise rotation, can I find out what is the torque experienced by the first current carrying conductor? So torque experienced by the first current carrying conductor will be equal to F vector into R perpendicular vector. Or I'll call it as force into perpendicular distance. So what is the force acting on the particle or the wire 1? IB into capital B into what is R perpendicular? It is A by 2. Because this is the point of application of force and this is the perpendicular distance, A by 2. So force into perpendicular distance. So this will give us IA into B into capital B divided by 2. Are you accepting this? Right? This is going to be the torque experienced by the first current carrying conductor. And the same torque, if I write it in the form of vector, I will write it as IAB into capital B divided by 2 in the direction of J cap with a negative sign. Why is it so? When you see it from the top, when you see it from the top, clockwise rotation is taking place. What are clockwise moments? Negative. So clockwise moments are always away from you. So here you are here. Okay. So something is away from you means it should be in this direction. This direction is minus J cap. Okay. Similarly, what is going to be the torque experienced by the second wire? It will be 0. Torque experienced by the fourth wire will be 0, and the torque experienced by the third wire will be equal to how much? IAB by 2 into B into, it is still minus J cap. Yes, because still the torque is going to act in the same direction, or else the system cannot revolve. So the net torque that is acting on the system will be equal to torque 1 vector plus torque 3 vector. So what is torque 1? IAB by 2 into B with a minus J cap plus IAB by 2 into B with a minus J cap. So what is going to be the net value? IAB into capital B, the whole thing in the direction of minus J cap. Now what can I call this AB as? AB is going to be the area. So I'll have this as IAB in terms of minus J cap. Okay, where we can call this current multiplied with area as magnetic dipole moment. So current multiplied with area is called as magnetic dipole moment. Okay, so if you want to write the torque in the form of vector, you write torque vector is equal to M vector cross B vector, where M vector is the magnetic dipole moment. Now see, M vector can be defined as the product of current and A if it is one loop. The same M vector can be written as Ni into A if it has N loops, where N is the number of turns. Okay, then that loop will not be anymore as a loop, it will become a coil. Okay, so what I'm trying to tell you from here is current carrying coils act as magnetic dipoles. So current carrying coils act as magnetic dipoles. Okay, now if you see, if you have an electric dipole and if you have a magnetic dipole, okay, for electric dipole, P vector is from negative to positive charge. Similarly, magnetic dipole moment M vector will be from dash pole to dash pole. It will be from south pole to north pole, because south pole in the case of magnetism is similar to negative charge in electrostatics. Okay. So listen. If you have a current carrying loop like this, then let's say the current is flowing in the clockwise direction. Then what is going to be the direction of magnetic field? This into the plane. It is into the plane. Right? When it is going to act into the plane, then I can say that that is going to be the direction of magnetic dipole moment also. Because when you take a magnet, right? When you take a magnet, then the magnetic field for a magnet outside it is from north pole to south pole, whereas inside it is from south pole to north pole. Right? So since this coil is receiving the magnetic field, then what you can say is it will behave like a south pole. Okay. In a similar way, if the current is flowing in the anti-clockwise direction, then here it will be in a position that the magnetic field will be out of the plane. Since this is the one which is releasing the magnetic field, it will act like a north pole. And this kind of a rule is called as clock rule. Okay, this is called as clock rule. So based on this, we can find out the direction of magnetic dipole moment easily. Is it clear? So you'll be able to understand one thing, that when you talk about a current carrying coils act as magnetic dipoles. That is why if you see the heading here, torque on current loop or magnetic dipole is what they mention. Okay, just give me a So torque on current loop or magnetic dipole. Is it clear? Right? So can we try out some simple problem based on this? See, for example, you can try out 4.10. Do it fast. 4.10 and page 156. So how to do the 10th one? Simple only. Done. So first part is easy. So you have a horizontal magnetic field of how much value? 3 into 10 power minus 5 Tesla, and its direction is from south to north. So you have a current carrying conductor which is placed carrying a current of how much magnitude? Current of 1 ampere, and in the initial case current is flowing from east to west. Current is flowing from east to west. So what is the force per unit length when it is placed on a horizontal table? What is the value of force? B into I into L. B is how much? 3 into 10 power minus 5. I is 1 into, so into L. So force per unit length will be 3 into 10 power minus 5 Newton per meter. Whereas in the second scenario, the current carrying coil is also placed in the direction of magnetic field. So theta will be 0. Second case, F is equal to 0, or force per unit length will be 0. That's it. Okay. Let's try out 4.5. Do that. So how much is, what is the magnitude of magnetic force per unit length? Wire carrying, so I into B into sine theta. Current carrying is 8 ampere. So 0.6 Newton per meter. Okay. Do 4.7. Two long and parallel straight wires A and B carrying currents of 8 ampere and 5 ampere are in same direction and are separated by a distance of 4 centimeter. Estimate the force on 10 centimeter section of a wire A. Two into 10 power minus 5. So F by L is mu naught I1 I2 divided by 2 pi d. Mu naught is 4 pi into 10 power minus 7. I1 I2 will give you 40 divided by 2 pi into distance of separation is 4 into 10 power minus 2. Correct? So 2 pi, this will get cancelled, this goes 10 times. So 200 into 10 power minus 7 into 10 power 2. Okay, this is the force per unit length. So this comes out to be 2 into 10 power minus 4. So F will be equal to 2 into 10 power minus 4 into 10 into 10 power minus 2. So 20 into 10 power minus 6 or 2 into 10 power minus 5 Newton. Are you able to understand? So in this chapter, you will mostly have to deal with exponents. 2 into mu naught by 4 is 10 power minus 7. Okay. So one last problem, try out 4.9. Can I rub this? Where did? Distance. They gave the distance between the wires as 4 centimeters. You understand? So both the wires are separated by distance of. What did you write mu naught as? The denominator you would have written 4 pi. It's 2 pi into d. So look at 4.9. Zero point. I do. So torque is equal to NIBA sin theta. N is how much? 20. I is 12. B is A is 100 minus 4 into sin. So 12 into 8 into 10 power minus 2. So 96 into 10 power minus 2, that is 0.96 Newton meter. Correct. So answer in this case is 0.96 Newton meter. Okay. So what all concepts are worked out? One is application of torque and ampere circuit law. So we try to complete them by tomorrow. Okay. Any other doubts from today's class? All are clear? On top it is into the plane, at the bottom it is out. Bottom na between. Loop எப்படி இருக்குன்னா current is in anti-clockwise direction. Current at the top is magnetic field at the top is into the plane. At the bottom it is. So here it out of plane. The out of plane, now what will you say? Which pole has the power to liberate the electric field lines? Another than not. Yeah. 1. .11. Direction of magnetic field they've given, no? It is from south to north. And the direction of field is from geographic south to geographic north. A very long straight current carrying conductor is placed in the field so that the current is initially carried from east to west. East to west means it is perpendicular. It is into the plane. Clear? That's it.
Minus I minus
The torque. Here we can wind up this.